So let us start. So mechanics, in the mechanics, right? Here there is something called generalized coordinates. So as part of mechanics, what we are going to learn is, one is the generalized coordinates. Generalized coordinates. The second one is holonomic constraints. Then third one is Lagrangian equation. The fourth one is Hamiltonian principle. Principle of least action. So these are the fundamental aspects. That's what we are going to learn, right? So these fundamental aspects. So in that, first and foremost is the generalized coordinates. So generalized coordinates, right? So the understanding of these generalized coordinates is, suppose if I take a simple case wherein there is a spring like this, and that for the spring there is a ball that got attached, right? I hope you understood the fact that actually, so this mechanics, whatever we are going to deal with is, when there are a system of particles that are moving here and there, so you wanted to identify the path of travel for each of the particle. And that's what is the whole intention of this particular topic. Got it? So, but Newton's laws, whatever it says, right? So Newton's laws actually, F equal to ma, that is the governing principle for the movement of any particular particle. Now, that particle actually, with no constraints, actually, it will be easy for us to solve with no constraint. But when there are constraints, then actually this concept of Hamiltonian principle is coming into picture. Now, we take a simple case of a spring connected with a ball. So this is the ball and this particular spring. Now, actually, so this is the vertical direction. For this vertical direction, this is making an angle of theta. Now, when this particle is moving here and there, then this spring is going to give an elastic, right? So this is an elastic spring. So the length can increase or decrease depending upon the force that is acting on this particular body. Let us say the initial length of this particular body or in this particular spring is L. Now, when this particle is moving here and there, let us say it made a displacement of u. Then L plus u times cos theta is minus of this. This is nothing but the y coordinate. Alright, so this is the y coordinate. So L plus u. So this u is nothing but the change in spring. So u is change in length of the spring. Now, if L plus u is the total change, and then minus of L plus u is the vertical direction which is in the bottom direction, and then the horizontal coordinates of this particular spring is going to be L plus u times of sin theta. So this is x is equal to L plus u times of sin theta. Got it? Now, from this understanding, whatever we have seen here, so these are the Cartesian coordinates. So x comma y are the Cartesian coordinates. And then, so u comma theta are the polar coordinates. Right? Now, if you want to find out the velocity in the horizontal direction in terms of the x, so this is dx by dt can be expressed as, so dx by dt, so L plus u times of derivative of sin is cos theta into d theta by dt plus sin theta into du by dt. Right? Now here, these are two different coordinate systems. So this is x comma y is the Cartesian coordinate system and u comma theta are the polar coordinate system. Now here, there is a factor of theta dot and there is a factor of u dot here. Right? Now, this is the Cartesian. So here, this is nothing but x dot. Now in general, x dot can be expressed as a function of theta dot comma u dot. Correct or not? In general, x dot can be a function of theta dot and u dot and even a function of theta and u also. Got it or not? Similarly, y also, if you take the derivative exactly in the similar manner, whatever you are going to get it is y is nothing but again a function of theta dot comma u dot comma theta comma u. So both are a functions of theta dot and u dot, theta and u. So this is also theta dot and u dot, theta and u. In general, here this is nothing but usually say if x is the displacement, then x dot will be the velocity. If theta is the angular displacement, then theta dot is angular velocity. So theta dot is angular velocity, right? Now here, from this understanding, you can express any Cartesian velocity can be expressed as any Cartesian velocity can be expressed as a function of theta dot, theta, t and u dot, u and t. So you will be able to express any Cartesian velocity in terms of this one with the dot, one without the dot and a function of t. Right? Now here in general these things, here also theta dot is there, theta is there, t is there. Here also u dot is there, u is there, t is there. Now x and y can be expressed with these variables. In general, what you can express is, so any Cartesian velocity can be expressed as a function of q dot, q and t. In general, you can express. So you can express as a function of the velocity of any other variable, as a function of the original displacement of the other variable and time together. So these three variables actually will together can represent a velocity in the Cartesian form. These variables we call as the generalized coordinates. So this is nothing but the generalized coordinates is q here. Got it or not? So in general, if there are 10 different variables are there, so all the 10 variables you can convert into a coordinate system where the Cartesian velocity can be expressed in terms of q dot, q and t. So this is q is a generalized coordinate for us. Got it or not? Understood? Understood or not? So this is in general, you can express any Cartesian velocity in terms of other variable velocity and its variable and the time together. So this is how you can express it. Similarly y dot, similarly z. So for any velocity of Cartesian form can be expressed into a general variable velocity and the displacement and the time together. So these variables we call as the generalized coordinates. So q dot, q, t are the generalized coordinates. So you can note down this. Why do we take q and q dot both? Because here actually when we took the derivative of it, so there is a theta dot coming and there is a normal plane theta also coming here. That's why these two together will represent that. Got it or not, Deepak? These two together will represent. Yeah. Got it? Because actually these variables actually we are going to use in the Hamiltonian principle. Clear? Note it down. The second one is holonomic constraints. So this holonomic constraints means, suppose, let us say there is a thread like this and there is a ball attached to the thread, and the coordinates of this is x comma y comma z. So this is the coordinate. Now let us say this is on a plane, then the coordinates are x comma y. Now the location of the ball is represented by the coordinates x comma y. So this location, now it is constrained by a length of L. That means this length, let us say this is origin, then the relation which is connecting this ball and the origin with a constant length of L is nothing but x square plus y square is equal to L square. So this is a constraint that is placed on this particular ball to move. That means even if I give you a force for this particular ball, this is allowed to move only in a circular path. This is not going straight forward even if I give a force in the uniform way. Got it? And this constraint will decide the ball to move in which direction it has to go. Correct or not? So this is a constraint here. This constraint, if you put it on that, now actually to represent this particular body at this particular point, now let us say if it is a three-dimensional coordinate, so how many coordinates you need? 3 different coordinates are needed. If there are n different particles are there, suppose there is one more particle attached to this, and this is represented with the letter L2. This is L1 and this is L2. Now here the coordinates are, this is x1, x2 and z. So x1, y1, z1. This is x2, y2, z2. Now here this ball is associated with the constraint of x2 square or x square plus y square is equal to L2 square. L2 square. So this is the other constraint. Now here, to represent these two balls in the space, we have actually 6 different coordinates. That is x1, y1, z1 and x2, y2, z2. So 6 different Cartesian coordinates are needed to represent 2 balls in the space. In general, 3n, where n is the number of particles. Three n coordinates are needed to represent n particles in space. Now, if there are 2 different particles are there, you need 6 different variables, that is x1, y1, z1, x2, y2, z2. Now, these 6 actually the Cartesian coordinates. Now, this ball is having velocity in the horizontal direction, vertical direction and the z direction. This ball is also having velocities in all the 3 different directions. Now, these velocities, if you wanted to represent, you have to play with 6 different variables. Correct or not? In general, if there are n different particles are there, you need to represent with 3n coordinates. So you have to frame all the 3n velocities and then you have to analyze it all the 3n velocities. Now that will be much more complicated for us. So to avoid that complications, the constraints, whatever you are going to put it on those particles to move, it will reduce the number of particles, so number of variables to a lesser value. That is, here in this particular case, y square is equal to L1 square minus x1 square. Y1 square is equal to L1 square minus x1 square. Now, if I express y1 square in terms of L1 minus x1, then x is x1 one variable, you can take it, and the y variable you can avoid, and then you can take as L1 square minus x1 square under root as another variable and z1 as the other variable. Now see this, we have only two coordinates are there, not three. Got it or not? So because of one constraint, we have reduced one variable. Suppose if I add one more constraint, then actually, so the other one actually I will represent x2 comma, so L2 square minus x2 square under root comma z2. Now this is again two variables. Now in general, if there are two constraints are there, two constraints and three n variables. So the total number of generalized coordinates that are needed are 3n minus m, where m is the number of constraints. So these many number of generalized coordinates are needed. Those are q1, q2, q3, dash dash dash, qm. So these coordinates will uniquely represent the space, all the particles here. Got it or not? So this is here in this case, there are four different generalized coordinates are needed to uniquely analyze these two particles in a space. Got it or not? See this here, to represent this particle, I need x1, y1, z1. To represent this particle, I need x2, y2, z2. Total, two particles I am representing. I need 6 different coordinates to analyze. Got it? So 6 different coordinates will give you the unique position and the unique velocity for each and every particle in every direction. Because in this space, you can have a 3 coordinate system. Now here, 3n coordinates are needed, where n is the number of particles. Here, this is 3, total 6 variables are needed. Now out of those 6 variables, here there are 2 constraints that are placed on this ball. So on this ball, x1 square plus y1 square is equal to L1 square. On this ball, x2 square plus y2 square is equal to L2 square. These are the 2 different constraints which will govern these balls to move in a specific direction. And those constraints together, right? So the number of equations that are needed are going to be reduced by a factor of m. So where m is the number of constraints. In this particular case, 2 constraints are there. Total 6 variables are needed. Out of 6, if 2 constraints are there, then 6 minus 2 is equal to 4. If you have 4 different variables, 4 different generalized coordinates, you will be able to uniquely analyze this entire system. Got it or not? So how we are going to reduce one variable is, here x1 is the one variable. Instead of y1, I can replace with the help of constraint as L1 square minus x1 square under root. And this is z1 as it is. So 2 constraints, 2 variables reduced. So these constraints we call as the holonomic constraints. Got it or not? Understood? Summary? Understood or not? Okay. So note down this. These are the holonomic constraints which will allow us to reduce the number of variables to a lesser extent depending upon the number of constraints. So ideally we should have been there with 6 different variables, but because of the constraints, but 3n is, see this, each position is represented with 3 variables x2, y2, z2. So total 2 different positions you need to represent x1, y1, z1 and x2, y2, z2. So these positions. So if I have one more ball, then I have one more 3 variables x3, y3, z3. Now total, if there are 3 balls, then actually 3n variables are there. Now out of that, if I have 3 constraints, then minus 3 is going to the effective number of variables that are needed to analyze the system. Got it or not? Right? So note down this. Note it down. Now, yeah. So Lagrangian is defined as, so from this actually, if you have any coordinates q, q dot and t. So these are the coordinates or the generalized coordinates for a specific body, right? So these coordinates q, q dot and t. Then, so kinetic energy is nothing but half mv square. Now this is if I have half m, v is nothing but q dot square. So this is the kinetic energy. This is usually represented with the letter T, right? And then the potential energy is usually represented with letter V, and this is a function of Q only. So let us say the potential energy of the body because of the movement from the bottom to the top. So this is nothing but mgh. So h is nothing but the coordinate z-axis. Here that is nothing but it's a function of q only. Got it? So in general it's a function of q. So in general it's a function of q dot. So kinetic energy is a function of q dot and potential energy is a function of q. Yeah, no, state space of control systems is a little bit different. This is a little bit different. So this here actually what we are getting is q dot actually is only the velocity. That is in state space technique. So we can have any variable. It may not be a displacement. Got it or not? That is more general state space equation. Got it? Okay. So here this is f of q and this is f of q dot. So Lagrangian is defined as L is defined as potential energy minus, so kinetic energy minus potential energy. Yeah, T minus V. So this is the kinetic energy minus potential energy for that particular particle. So this is what we define as the Lagrangian. So if there are only one variable, this is T minus V. If there are multiple variables, then the sum of the potential energy, sum of the kinetic energy, you have to subtract it. So L is in general sigma, so of mi into q dot I square minus V of, or just V. So V is nothing but the potential energy here. So sum of the kinetic energy minus sum of the potential energy of all the particles here. Now here V of Qi, then this is the sigma, right? So this is how you will be defining the Lagrangian. In general, this is T minus V. So T is the potential energy, T is the kinetic energy, V is the potential energy. This is defined as L. So Lagrangian actually he has given this one. So from this actually Hamiltonian derived a principle, that is the principle of least action. What he says is d by dt of dou L by dou Q dot minus dou L by dou Q is equal to 0. So this is what we call as Hamiltonian principle of least action. Principle of least action. This is Hamiltonian principle of least action. Now, this is the fundamental principle. It's like a Newton's law for us. So, Newton's law actually, he is talking about only the change in velocity, which is nothing but the acceleration. If there is an acceleration, then you are going to get the force. Now, those force equation is the fundamental principle for us to identify the path of any particular particle. Now, that is applicable. So, or actually, you will be able to solve with the help of Newton's laws if there are less number of constraints and if there are least number of variables that are involved in it. Now, here actually, he has given a different approach. He is not talking about the force. He is not talking about the acceleration. He is talking about the generalized coordinates Q and Q dot, which are nothing but the Cartesian equivalent in another coordinate system, right? So, you can analyze easily with the help of Cartesian coordinates, but that analysis actually, as the number of particles goes on increases, then for each variable you have to have 3 different variables. Then in total, it will be 3 variables you need to analyze. 3 and if you subtract the number of constants, you are going to get the generalized coordinates. So those generalized coordinates with the help of only energy equation. So this is the fundamental equation of the Lagrangian. So Lagrangian is nothing but the energy equation, which is the difference between the kinetic energy and the potential energy. If you know this L, you will be able to derive the equation of the path of the particle. So that equation of the path of the particle you will be able to derive with the help of this Hamiltonian equation of least action. Got it? So this is what we need to understand. This is very important to understand. Not only from this, so directly from this equation only, the UPSC actually is giving questions based on this understanding. So here there is one Q dot, which is nothing but this is the velocity. Q dot is velocity. This is displacement. And L is Lagrangian. And is given by L is Ke minus Pe. Right? So this is time derivative. So this is going to give the same analysis whatever we are getting with the help of Newton's laws. Same thing we were able to get even with this as well. Got it or not? Right? So that's the only advantage about this Lagrangian and Hamiltonian equations. So these Lagrangian and Hamiltonian equations will come into picture if you wanted to analyze the particles are n number. So if there are many particles that are there, then each particle actually you can take as a separate unit, and then each can be represented with a different set of coordinates, and those set of coordinates you can further reduce the number of variables to the generalized coordinates, which are the least possible constraints, least possible number of variables you can put it, and then from there find out the kinetic energy, find out the potential energy, subtract between these two, and then for that you substitute in this equation, you are going to get the equation of motion for that particular particle. Got it? Understood? Or do we have any questions? So here there is a dot, note it. Please repeat. Okay. So here actually Newton's laws actually it will give the equation of path of the particle, right? So Newton's laws it will straight away give. Suppose if I take a spring, right? Spring action, if you take it, this is a spring. Now Hooke's law states that, so this is the force is directly proportional to the spring constant here, right? Or the displacement that is moved is proportional to the force, or nothing but A is directly proportional to x, or Kx is equal to m into d square x by dt square. So this is the equation of motion. This you are able to get it only with the help of only the Newton's law, that is the force balance equation. Yeah, so you can expect problems on this. Okay. So here, with the help of force balance equation, that is the force that is applied on this and the spring constant bringing is back. The force that is applied is nothing but MA. So MA is equal to the force that is dragging back, that is Kx, right? So M into d square x by dt square is equal to Kx. This is nothing but, this is in the opposite direction. So this you can write it as, so minus Kx, or M into d square x by dt square plus Kx equal to 0. So this is the equation of motion in case of a spring constant. So this, with the help of Newton's law actually, you will be able to derive it. The same thing you will be able to derive even with the help of this Lagrangian and Hamiltonian equations. So Lagrangian and Hamiltonian equation, it doesn't talk about the force, it talks about only the energy. That is the difference. So there with the help of force, here with the help of energy. This energy taking as the variable, it will simplify our work when there are n number of particles that are involved in it. Got it or not? Energy is a scalar, so that's the reason actually it will give you very flexible manner to derive. So for now actually you may not find actually this is very great advantage rather than Newton's laws. But if there are multiple constraints are involved, multiple particles are involved, suppose if there are 10 or 20 particles that are involved, then that time this method of finding out with the help of Newton's laws will be very complicated. There actually energy, if you take as a possible variable, then the method is completely simplified to a lower extent with the help of Lagrangian and Hamiltonian equations. Got it? Understood or not? Samran, do you have any questions? Okay. So now actually the same equation with the help of Lagrangian, by taking as the energy as a variable, we will bring the same equation. Just look at here. Note it down, all these things. Okay. So exactly. So this is a mathematical tool only to solve complex level of particles. Got it? So if there are many number of particles that are there, then Lagrangian and Hamiltonian equations are the best suited for us to analyze. This is simply a mathematical tool. Got it or not? Got it? Now let us take a spring like this, and then on this spring, so there is a force that is applied. Now if the force that is applied on this particular spring, then it is getting certain potential energy and the kinetic energy. So there is some potential energy, there is some kinetic energy. So kinetic energy, when this particular particle is moving like this, so because of the spring action, then the kinetic energy will be of k into x dot square. So of m into x dot square. Got it? Got it? Okay. And then the potential energy will be, so you are going to get as for a spring constant of kx square. So this is the potential energy. Now the difference between this potential energy and the kinetic energy we call as the Lagrangian. So Lagrangian L is equal to T minus V. So T is the kinetic energy and V is the potential energy. Now kinetic energy is of m x dot square. So x dot is nothing but dx by dt. So x dot is equal to dx by dt, which is nothing but the velocity. So this is the velocity. So m into x dot square minus the potential energy of kx square. So this is L. Now this L value, what we have got it, so this is the energy difference between these two. Then what we are going to get it is the principle of least action, that is Hamiltonian principle of least action. So what it says is d by dt of dou L by dou Q dot minus dou L by dou Q equal to 0. So this is the fundamental principle of least action. Now this dou L by dou Q. So here actually in place of Q we have the variable x and x dot, right? So x is Q and x dot is Q dot. Now for this actually dou L by dou Q dot, dou L by dou x dot, if you take it, so this is, take the derivative of it with respect to time, then this will be 2 times of m into x dot divided by 2. So this is mx dot. So mx dot is dou L by dou x dot. Similarly, dou L by dou x, you can calculate, this is dou L by dou x is minus 2 into k by 2 times of x, right? So this 2 will cancel, minus kx. So this is dou L by dou x and dou L by dou x dot actually we have calculated. Now d by dt of this one, that is d by dt of m into x dot minus, so dou L by dou x is minus kx is equal to 0. Right? So here m is anyway constant, x double dot plus kx is equal to 0. Now this is exactly what we have got with the help of Newton's laws of motion. Here if I put it in our standard method, that is m into x double dot is d square x by dt square plus k times of x is equal to 0. So this is what actually we have got with the help of Newton's laws. So the force and the movement, that is mass into acceleration. So ma is equal to minus kx. So this is the equation of motion. With Newton's laws. Got it? So the same thing actually we have just drawn. That is Newton's laws, what it says is ma is equal to minus kx, or ma plus kx is equal to 0, where k is the spring constant. So where k is the spring constant and a is the acceleration and m is the mass. Got it or not? Understood? So we have got with the help of Lagrangian and Hamiltonian equations, whatever we have got it here, the same thing we have got with the help of Newton's laws as well. So which essentially do the same purpose, but here the variable is energy, there the variable is force. Clear? Understood? Or do you have any questions on this? Understood? Any questions? Anyway, so I am going to take it up. So here actually the questions that are asked are based on this principle for different kinds of the problems that we are going to deal as part of mechanics. So like actually cycloidal movement or simple harmonic motion or the spring constant level problem or the rolling motion. So all those motions actually you will be able to derive with the help of Lagrangian and Hamiltonian equations. But first of all, you have to understand, so you have to understand the concept here. That's why actually I have taken the simple problem here. So in the next class, I am going to take up the complex problems. Clear? I hope you understood the concept. Here the summary is what is a generalized coordinate and what is holonomic constraint, what is the Lagrangian and what is the Hamiltonian principle. What we can do with the help of Lagrangian and Hamiltonian principle. So that's what actually we need to be doing it. Got it? So if you understand that fact, then actually in the next class I am going to deal with only problems based on this understanding, and that too a little complex level problems actually I will take it up. Clear? If you have any questions, you can let me know. Okay, so that's all for today. So in the next class actually I am going to take it up on Monday. I am going to take up the problems based on Lagrangian and Hamiltonian principle. So with that, the mechanics will get over, but I will take the complex level of problems. Clear? Okay, yeah. So thank you. Good night.